should have enough time. You should be able to do almost everything. It's primarily as a check on the cost, right? So if you're nowhere close to the cost limit, which is possible, then you're already fine, right? If you're doing just pixels, as long as you're accounting for the readout, you should be fine as well. Okay, the readout's a real expensive part. As long as you're accounting for the readout cost, you should be fine as well. The tricky part is the strip detectors. The strip detectors, you can lay an end-to-end as long as you want. There's no need for it. So several people have questions about it, just to be clear. The strip detectors, they come in strips, right? You can lay strips end-to-end for as long as you want. That's no big deal. You have to leave room above, and so these big flat pieces of silicon, so the parts above and below them have to be left free so that heat can dissipate and the air can flow through to disperse it. Okay, end-to-end is no problem. If you have a weird thing with like one that's perpendicular to that, that's also no problem. Very little contact points, so it's fine. But you just can't stack them like this, long ways on top of each other without a 2 centimeter space. Okay, so the one thing that will mess up your channel cost is that you can only build these wafers 10 centimeters long, each wafer, which means if you have a cylinder, right, the number of channels is not just counting this way, how far you are along the cylinder, but you also have to break it into 10 centimeter segments. So it may drive up the cost on your readout for strip detectors. That's the primary thing to watch out for. Everything else should be fine. So you should be able to, I mean, maybe I did more than I can chew with this project attempt, but anyway, you should be able to finish more or less everything, and the only danger is if you're near the cost limit. And you don't have to be near the cost limit, right? This is not one, you can save the money and spend it on your color render or something, you know? I actually have no idea how big your cost limit needs to be. And also people with different energies that they're going for anyway. So, so the point is, the point is you should be mostly done, okay? Possibly I may have to push this deadline a little bit farther, which is not something I typically want to do, but I may need to. There's a lot of things going on. And so, should that happen, should be no big deal. Like, this should be basically final check on the cost and a final look around to make sure that your spreadsheet does what you think it does, right? My program represents what I think your spreadsheet does. So this way it's a nice check. You're actually sure of what you're telling me now, and that to me is that's really why I did this. So you can see what I think what I'm going to see, and that way we can be in agreement about what I'm going to see. Okay, Kyle.
Could you just check me
that's my program. Since all of you got those from me, and that's why I can do it, I just have to remember to do it. All right, then. Is that your question too? Is that your question too? Oh,
okay, I'm still there.
Then I'll add it. Well, that's an interesting question. What I would do is this. You send me an email saying, Dr. Dom, such and such a functionality is missing, right? In the meantime, you do something to make sure that things look sense. For example, if you want segments of spheres, and you make, wait, is spheres not hyperbolic one? Oh, it's not anymore, okay. If you're doing a segment of spheres, then you can put in a sphere, and then just remember it's only this part of it, and see is that part of it where you want it to be, right? So you can still do some checks, and then while you wait for Dr. Dom to get up to speed, which may take a while. You know what? I will work this part out. You guys should be mostly done. Aren't you mostly done? Okay. Well, get mostly done. How about that? Okay. Good. I said Tuesday night because Wednesday night you should be working on the next homework, right? I figured. So I said Tuesday night seemed like a sensible compromise. Provided I can actually get this stuff done, which depends on a lot of things. Some of them maybe that's right. And also stupid rep letters. Anything done with those stupid rep letters? Yeah. It affects the channel count because if you have, imagine you have a strip of silicon like this, right? And you want to do a channel comment. Now you're doing strips, right? So if it's a single strip especially, well, this affects double strips too though. If you have strips going this way, right? So you just take the distance from here to here and multiply by the channel density and you'll get your number of channels, right? But now you have to realize these strips cannot be like 20 meters long. They can in fact only be 10 centimeters long. So now the number of strips is the number of strips in one, number of channels, the number of channels in one of these, times the number of 10 centimeter wafers you need to make along the end. Okay, now you don't have to put that in the spreadsheet. Okay, so what happens is this: you put everything in the spreadsheet. I program this actually wasn't the hard part. I already did this part, and I'm just trying to put the rest of it running. Apologies. I actually got a lot done last night, but most of the time I was spent writing recommendations. So, but the program will break it up into the silicon pieces for you. Like you put in a cylinder, it'll break that up into wafers of silicon. You put in something long, it'll split it up into pieces for you. But still, you have to realize that there's a maximum of 10 centimeters. So if you have long strips of silicon, the channel count is going to be pretty high, right? If you just estimate the channel count by taking this and multiplying by the channel density, you're going to need to multiply that number by the number of 10 centimeter segments, which could be quite a few, right? So it's going to drive up your channel count for a strip detector. If you're doing double-sided, that's really only going to affect one of the sides, right? The other side is already going this way. Yes? For pixels, it won't affect it because the pixels are just by area anyway. You just have to be area. So it's only the strips that are going to be affected. Pixels, you just take the area multiplied by the channel density, and that gives you a number of channels, right?
Oh, and then so for the pixels calculating the cost, you can just do like however long you have it.
Yeah, pixels easy, just do area. But like if you have a cylinder, for example, right, you probably just took the circumference of the cylinder multiplied. Now you actually have to think, what's the length of the cylinder, divide that by 10 centimeters, and multiply your number of channels by that, right? That's how many channels you actually need. Which is actually good in some way. It drives up your resolution, because otherwise one giant strip running the length of the detector is going to get hit by a lot of different particles, and that's not efficient anyway. So it helps your detector anyway to design it that way, but there's also technical limitations. Say it one more time. Oh yeah, you can measure some discs, and again, there's just a limit. So if your disc is a meter long, then you really need to break it into 10 segments. Most things you can do by just multiplying, right? You take the length of the strip you're looking at and divide by 10 centimeters and multiply whatever you had by that. For the case of this, well, so for a disc, you would probably take the outer circumference. You take the outer circumference multiplied by channel density, right? You would have the strips going this way probably, right? So you take the outer circumference multiplied by channel density, then take the radius divided by 10 centimeters, and that's how many pieces you need radially, and then multiply those together. Okay.
If that's just single side, because it's something too much.
Yes. Just put in exactly whatever I put in there.
Nope,
that
wait, sorry, that's not.
So for the spreadsheet, and I think I called it resolution, right?
I can't do a million.
Yes, okay. So slash, right? There's a slash. Yeah. So in the spreadsheet, you should just put the resolution. By default, you should put 20 per thousand for the strips, and whatever it was, 10 to the 8 or whatever it is for the pixels. And just put in the number straight out of the table I gave you. But you may make the number lower to save money. Remember how I mentioned that? That's the main reason there's that column there at all. And to enter the strength of the magnetic field. So for if it's a solenoid, put a number in Tesla in that.
So I calculated it using what I
That's
wanted.
the main thing from that. The rest then, by default, just put in the maximum that I have in the table.
Something like that.
And then only lower it if you're trying to save money.
Sorry, I have it as a centimeter.
Okay, good. Any other questions on that? So, like I said, there may be a delay in the program. It's like almost done, but it was 2:15, and then Ezra was crying. And so, anyway, so I think it's almost done, but who knows, right? It's computer. So, the code's written, though. It just needs to, actually run. So anyway, we'll see. So I have some hope, but a lot of things are going on today too, so I don't even know. Okay, point is, get everything mostly wrapped up. Okay, then we can use this as hopefully a fast cross-check. And if it takes a little while to get the kinks worked out, it'll take a little while to get the kinks worked out. We'll also run it. Okay, next thing, remember please, that this Friday, what happens? The exam redo correction thingy is due. What's that call it?
Correction.
Second chance Redemption. Yeah, exam redemption. For some reason, all my classes always end up with mechanisms with like religious overtones. The redemption quiz and homicide indulgences. Which, by the way, is exactly the right.
That's me and Matt.
So this redemption question, if you like, is due on Friday. I want everyone to turn it in, and I want everyone to get it right. Okay? Like, to me, there is no reason why that should, okay, there's a few small reasons, but like, I don't want anyone not turning it in. That is the wrong thing to do. You're like, I don't know how to do it. Great, find someone to tell you how to do it. There's 45 people in this class, because the other class has the same question, right? They don't have your numbers, but they have the same question, so they can tell you how to do it, okay? I want you to turn in this paper with the right answer on it, and the work on it. Okay, that is the purpose of this paper. So, and then I can give you points for it. So please, everyone do that. Got it?
Got it.
Okay, good. Now, the one restriction is I did tell Dr. Hopper not to help with this. So, he's probably the only other staff member in the school who'd be able to help because it's not just knowing, having taken this before. You have to really like taught it to be able to do this kind of problem. It's pretty tough problem. So, probably the only one else at the school who would be able to help you. So it's okay. There's 45 of you plus Dane. You're fine. Oh no, 44 of you plus Dane. Still fine. Okay. Okay, so work together. Like, work with each other. Get the answers from each other. I want you to do this. I want you to write up the right answer and turn it in. Okay? Alright, good. Moving on. Next week, Monday and Tuesday, I will not be here.
Oh, no.
You will still be here.
Nice.
Why?
Okay? On probably Monday, we'll see if it has to be Tuesday. I know one of those days we'll have a quiz. On the other day, there will be an assignment. There will be something for you to work on in class. Okay? Andrew or Julie or someone will be babysitting you. But you'll have something to work on in class. Okay, then we'll come back. I'll be back on Thursday and we'll continue. This is just to make sure you know you're still to come here. And one of those days will be the quiz. We'll see how things go this week. Speaking of which, let's start some physics. Alright, so now is for the fun part. This is my favorite part of all of particle physics.
I swear, he says particle color.
Feynman?
Okay? We have a cast of particles, right? Remember our particle sheet that you looked at? We have a cast of particles, and we have these interactions, and we know which interactions are impossible, which is great, and which ones are possible. That part all on fine, right? Okay, so now, and kind of try and dredge that up for your memory, because you do still need that, because it's been a while. So now the question is, how do particles interact? And that's the important part.
Ow. That was my answer.
That's kind of a funny reaction. Go ahead. So, the way to describe how particles interact is through math. The math of it is horribly math, like really, 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 really math. As a result, I actually later on will give you a real quick overview of how that works, but let's not even think about that right now. There's a horribly difficult thing to do with this math. Here's the thing: you end up having to do this ridiculous. And you know what a Taylor series is? You have to do this anyway. It's very ridiculous Taylor series. You end up with like all these terms to keep track of. It's very, very complicated, easy to mess up. So there are two options when you have something that's really, really easy to mess up. There were two different Nobel Prize winners. They won the same year, who came with two different solutions to how do you do such a giant complicated computation without messing up. One was Julian Schwinger. Julian Schwinger was the guy who got his PhD at 20. He decided that the best way is to just not mess up. Because he did it, why should you? And so he just run through the math and boom, there's the answer, no big deal. Okay, the other person who was no less smart, nonetheless had a more intuitive approach to things, and came up with a way to not mess up by coming up with a mnemonic device by which you can remember which terms went where. And the mnemonic device takes the form of pictures that you draw. And the pictures that you draw turn out to be a really good way of visualizing how particles interact with one another. Even though they're not pictures, they're just math, they're just representations of math expressions, they nonetheless are very useful for visualizing things, such that today the majority of particle physicists don't actually know how to do the math anymore, they only remember how to draw the pictures. They are all line diagrams.
You're 4.
And E looks like she's about Okay, Feynman diagrams are named after the great physicist Richard Feynman, who shared the Nobel Prize with Julian Schwinger and I forget his first name, Tominaga, for their work on quantum electrodynamics. And Feynman is known for a lot of things. He's a very brilliant man, but one of them definitely is, as you mentioned, the Feynman diagram, which is just a really nice way because it allows you to do a lot of stuff to talk about particle interactions without having to do the math by just drawing the pictures. So we're going to skip the math.
Yes.
And we're going to do the pictures.
Yes.
So, here we go. Here are those Feynman diagram rules. We'll start with the basics. Wow. A fermion looks like this. Oh, not quite. Hang on. And there's an arrow in it. Notice the arrow goes in the middle of the line, not the end. The middle of the line is the standard place. Okay? And the fermion is labeled. Give me a fermion. They're all on that front page. What?
Electron.
The charm quark. Okay, the charm quark is the symbol C, so you just put the symbol next to it. Right? Okay, you put the symbol next to it, not at the end. You put it next to it like this. Okay? And the arrow goes in the middle somewhere. Okay? Now, an anti-fermion looks. Give me an anti-fermion.
Tell me, is the arrow backwards?
What?
Positron.
Okay. An anti-fermion looks like
Yes! That makes it so easy to remember.
What's the difference? The arrow's pointing the other way. One points to the fermion, so like regular particles point to the right, antiparticles point to the left.
So wait, if it was like an electron, would you put a P instead of an E?
If for an electron, you would put an E minus next to it.
Okay.
Oh, for the antifermion? Or you mean a positron?
Yeah, like...
Positron, you put E plus, that's a symbol for positron.
Okay.
Okay, so this is how you draw
I'm
that.
really good with this.
And a photon, you would draw like that. A wiggly line, no arrow needed, and the symbol of a photon, which is gamma, next to it. Now you should have no trouble remembering that. The photon symbol is gamma. It actually is not because of relativity, because of the gamma factor, it's because of gamma rays. Gamma rays are photons, they named them before they knew what they were. So that's why it's gamma. Okay? Alright, so those are your basic pieces. Now, these diagrams are not pictures, okay? They are topological diagrams. That is to say, the only thing that matters is how the lines line up, okay? That is to say, if you have a particular, okay, let me start by introducing the vertex. So the most important thing is the vertex, okay? The vertex means the point where the lines can connect to each other. It's the only way the lines are allowed to join to each other. And the rule for the vertex is, here's a standard vertex. It looks like this. Let's take an electron for an example. Okay. This is a standard Feynman vertex.
How does it look to...
What did you say? Oh, it is. Okay. So, no, it's not. I don't know. I don't think this stuff is that hard. I think it's awesome and fun and easy. But like, I don't know. I must have a particular thing for little pictures with squiggly lines. Maybe because I can't draw any other kind of picture. And so I'm not sure. But this always came to me really, really fast. The first time I did this, I tried to teach it in a day. I discovered that a week is better for it. So, but because it doesn't click as quickly for some people, and that is fine, by the way. I'm not sure what it is about my brain that likes little pictures like this. But I think that's fine. Okay, so first of all, let's talk about the rule, and I'll tell you how to read that. The rule is a vertex must be 2 fermions and 1 boson, where a photon is a type of boson. We'll have other bosons later. The bosons are at the bottom of that first page. There's only a few of them. There's basically the photon, the gluon, the W, the C, 4 bosons. We'll get to the other bosons in a moment. We'll focus on photons right now.
There's no boson there.
This is a boson. It's a photon, right? Photon.
It's
the very first boson.
Okay, we got it. We're all good. Okay, so, and then we need all lines,
I can't do this.
sorry. Let's try this again. Fermions must have the same flavor.
They must be the
Stupid word. Stupid physicist. Flavor, yes. What does that mean, flavor?
They taste
So
the same.
flavor means is this. An electron and a positron, for example. Or let's say a muon and an antimuon. Are they different particles? Sure they are. But they're really similar because they're antiparticles of each other, right? So we use flavor to mean any particle plus its antiparticle. So for example, electron or positron are the same flavor, okay? Or up or anti-up are the same flavor, okay? Now up and down are different flavors. So it's just a particle or its antiparticle are the same flavor, okay? It's a stupid word that someone clearly came up with offhand late at night, and no one ever bothered to change.
Let's make it
So,
flavor.
So now we have flavor. The only really good thing you can say about it is that it allows for some really creative food-based desserts. So the fermions must have the same flavor, and then the arrows must point. Let's say, I don't know, along the line. These are probably easier to show by showing you what's not allowed and what is allowed. Okay? So 2 fermions, 1 boson. So here's something that's not allowed. Okay? This one is bad. Red, I don't remember. Green it is. So bad.
Why is it?
Okay? Why is it bad? Because I have 2 bosons in that vertex and you're only allowed 1.
Oh.
Okay? You can only have 2 fermions, 1 boson, exactly.
Wait, does that mean you get an unlimited amount of baryons?
Unlimited amount of baryons. I'm not quite sure what you mean.
No.
But maybe. The main thing is that you can't draw a vertex like this, okay? You have to exactly 2 fermions, 1 boson. When I say fermion, I mean fermion or antifermion. Sorry. Or antifermion. It's fine too. But it has to be 2 of them exactly. Notice here, there's 1 fermion and 1 antifermion. That's cool. The problem is there's 2 bosons. Okay, for this one, fermions must have the same flavor. That means, I'll draw it over here, that if you have something like this interaction, you see this? This, also forbidden. Why?
Because I can't see it.
Because here's one flavor fermion, the electron. Here's a different flavor, the muon. Electron and muon are different flavors. That's not allowed. You may not change flavor. That's the word for it. You may not change flavor at a vertex. I know, right? These vertices are flavor conserving. That's actually the word for it. Flavor conserving, yes. That's actually how they say it.
I wish my gun was like that.
Or if you like some, flavor ag. Yeah, I know. Don't worry about it. You'll actually see why that makes sense a bit later. Okay. And then arrows just point along the line. So these 2 here are okay though. Why? Just not ignore that side. These 2 are okay. They're the same flavor, right? Electron and positron are both of electron flavor. Right? So you see what I mean by flavor? The particle, the antiparticle, those are both the same flavor. Okay, good. Let's hold it here. Okay, so then arrows just point along the line. Here is something that is not allowed.
You
See that? You see it okay? Why is that? The arrows have to point sort of in the same direction along the line, right? In other words, the head of one arrow points to the tail of the next arrow. They cannot point into each other or away from each other. They have to point all continuously along the line. So it is possible to have a fermion line that looks like this, but the arrows have to point like that. You You see, they have the point so that everything is flowing along the line. As long as they do that. So this is not allowed. But this, where the arrows point into each other like so, is fine. Fine.
So you're saying a fermion can't be made into an antifermion?
Not like this, anyway. This interaction, this specific vertex is not allowed. I haven't actually told you how to read these yet, but I don't have a question. All right, so let's talk about how to read these. Remember, these are not graphs; they're not pictures. The good analog of what these are is like Lewis dot structures. Your favorite, right? Lewis dot structures, are they pictures of atoms? They are not. Atoms do not look like that. But they're useful ways of dealing with the orbitals and the bonds and so forth that let you figure out the properties of things. That's how the diagrams are. They're not pictures of the interaction, but they allow you to figure out how the interactions work. Or like those benzene ring things they do in organic chemistry. Right? So that's what these things are too. They're not pictures, they're just useful ways to visualize. And they're much more fun than those dot structures. All right, so here's how to read it. Time goes from left to right. Warning, half the physicists in the world have time go from bottom to top. Why? Because they suck. No, that'd be even worse. That's the opposite direction of an axis. Right? Axis go, the y-axis goes this way. So, oh, crossword puzzles, you're right. That's literally fundamental. Right, you got me. All right. So time flows like an arrow. No, time goes from left to right. And so the yes. So this axis is not an axis. It doesn't mean anything. Time goes from left to right. Like I said, whatever you're looking at, this includes the Wikipedia diagrams. Those are drawn bottom to top sometimes. Look, it's just anyone can post on that thing, right? So there's no quality control on this.
So wait, how do we know if we're reading it right?
How do you know if you're reading it right? You figure it out.
This one on the side can't actually have things that go backwards.
Something wrong with things going backwards. What? Something wrong with things going backwards. Yeah, no problem. What? Okay, no, we'll get there. Okay, so remember, these are not literally pictures, so keep that in mind. Don't take them too literally, but they're really helpful. So I often will speak about them as though they are actually like happening, but then every now and then someone will go, okay, but that part doesn't happen, you know? So like remember, these are still just mathematical mnemonics. But what does this say? Tell me, if this is time progressing this way, what does it say happens? Go ahead, Nick. Okay, there's an electron going along. I don't think it's really sensible to say that this is a different electron. I think we can call it the same one. So an electron's going on, and then it releases a photon, right? The word for that is, it does what's the photon? It emits a photon. So this particular diagram we can call an emission. Okay? People often find it helpful to categorize different ways, but there's only a few ways you can draw this vertex. So. All right, these are the only rules on the vertex. The nice thing about these, then you guys do any like topology or cohomology or stuff in that? No, not yet? Okay, well, you will, probably some of you. But, yeah, or graph theory. We don't have graph theory anymore? We don't have graph theory anymore? Okay. Do we? Oh, it's the spring. Okay, well, anyway, you guys say graph theory? No? All right, well, what do you do? The idea of it is that it's not like the distances between things don't matter. What matters is what is connected to what. Okay, that's a topological issue. So let's say it doesn't matter how far they are, where they are. That doesn't make a difference. But what matters is what vertex connects to what vertex. Okay, so the lines in between you draw however you want. It's the vertices that are important. Okay, in particular, rotating the diagram is perfectly legal. In other words, if this is legal, you rotate it in any other way, it'll still be legal. Or twisting the things around, right? If you just take it, switch these two around, switch that way, rotate the whole thing. Everything is as long as it's the same vertex, it's still legal. So let's take this, for example, and rotate the whole thing, say 60 degrees counterclockwise. If that's the case, you end up something that looks like this. Ignore this part, by the way.
Oh.
Okay, right? Same diagram rotated. You See it? Okay, good. Also perfectly legal diagram. So I'll describe what's happening. I go.
A photon and an electron collide and produces an electron? Or a higher energy electron?
So what would you say the electron does to the photon?
Absorbs.
Good, it absorbs it, so we can call this absorption. Did you know that in, if you do like vacuum engineering and stuff like that, which is common in a lot of physics experiments, there's actually 3 different ways of talking about absorption. There's absorption, adsorption, and absorption.
What?
Why?
They're spelled slightly differently, they mean different things. It's horrible.
Oh my
So
God.
horrible.
Oh no.
I don't study vacuum structures. It's like really complicated. Vacuum engineering is very difficult.
So don't spell absorption wrong.
So anyway, I don't remember which one the right one is. I just gonna call it that. Okay, good. Now we can do it again. What's another way we can rotate this? How about I take the whole thing and rotate it? I take this, I'll rotate it 120 degrees this way. That's to say, to put these guys up front. Now notice, because the arrow is supposed to point along the line, it ends up pointing like this, right? Now, if this is an electron, what is this particle?
An anti-electron?
This particle has to be a positron, because I reverse the direction of the arrow, right? So remember, since they're the same flavor, that's all that matters to the vertex, right? But when the arrow points backwards, it turns into an antiparticle.
Wait, doesn't that violate the rule the arrows must like point along the same line?
No, the arrow goes like that, right?
Oh, okay.
It flows through the line like that. That's what I mean by it. Okay? All right, someone tell me what is happening here. Go ahead, John.
Magic.
Good. Electron and positron collide, they form a photon. Because electrons and positrons are considered as stuff, they make up stuff, and photons do not make up stuff. Therefore, we think of this sort of as a loss of stuff, and the word for it they use is annihilation. That's right. Annihilation could be defined as the loss of stuff, although it tends to be a little bit more dramatic than that. So that's annihilation. And after years of teaching this class, I can now spell that word. Yeah, right? And there's an H that no one pronounces. Annihilation. I know, right? Yeah, because why would you pronounce it? It's because it comes from the root word of nihilism, or nihil, the root, and then they stuck the an in front of it. So an, nihil. Anyway. So this is called annihilation, and you may notice that this would happen with any fermion would form this diagram, right? Because we've allowed, and we haven't done anything specific to fermions. There's actually very little that is. So an electron, positron, a muon, anti-muon, up and a down quark, an up and an anti-up quark, right? And so the upshot of it, the quick version is that if you have matter and antimatter, you get mutual annihilation, right? You get conversion into energy. They often refer to this as mass energy conversion. Right, if you have 2 fermions, what would be the problem? Today suggests what if it were 2 fermions? The arrows would screw up, right? If you have 2 fermions like this, no good. See that? With the arrow.
They look like that's helpful.
That's why the arrow rule is very important. Okay, so that's absorption, that's annihilation. One more, let's take this and mirror image it.
Decay.
Okay, notice I'm careful that the one that points to the left is an antiparticle, the one that points to the right is an antiparticle. And notice even though they're in a slant, you can figure out which one's pointing left, which one's pointing right. Okay, the slant doesn't matter. Yes. Does not matter at all, because it'd be perfectly legal diagram switch the other way, right? So go ahead, tell me what's happening next.
So you have a photon that's going along, and then it splits into a positron and an electron.
That's correct. Photon splits into a positron and an electron, and we refer to this as?
Decay.
We don't call it decay when it's a photon.
Dang
We
it.
call it decay when it's other things, but photons are weird. I mean, photons don't decay. So we use another word for it. Scattering, this is not scattering. Scattering is 2 particles in initial state. It's called what? Production? We actually do call it production. Production of what, though? Production, it produces matter. Well, whenever it produces matter, you notice how it has to produce that. Is that it has to produce how many particles? Two. And what do those particles have to be?
Anti and
One fermion, one anti-fermion of the same flavor, right? That has to be how it works. So because they always come in pairs, this is referred to as pair production. It's not referred to as creation, which really makes sense to be paired with annihilation, but I think people thought that was a little too theological. So, pair production it is. Anyway, why don't you just call this pair destruction? I don't know. Okay, those are the words we use for it. Okay.
Whenever you say pair production, I think with someone like taking a stick
Alright, so, now we're ready. Okay, now these are all the same thing. I'm drawing them up here as examples of what you can do with the same vertex. Okay? Because time always goes from left to right, but you can rearrange the lines any way you want, the same vertex can represent different things physically. Okay? So now it's really just a matter of taking those vertices and chaining them together. So we are now ready to embark on baby's first Feynman diagram. Ready? I mean, that's for you guys. My babies have already finished Feynman diagram. So, here's how it works. You're going to be given an interaction. I will give you the simplest one I can think of.
What?
I don't remember what this was called.
What?
Bob must have.
This is
This
isn't Feynman.
Okay, don't worry about it. This is so sexy. What does it say? This is an interaction. It says an electron and positron interact and create an electron and a positron. Okay, which is maybe not that exciting, but it happens, right? You have to admit that. So, what you do is this. Everything in the initial state, you write those particles going down one side. Everything in the final state, you write those particles going down the other side. The order does not matter, although some orders can be easier than others. It doesn't actually matter. Okay, your job now is to connect from the left side to the right side, following all the rules of Feynman diagrams. So basically, you're going to start with these. These are fermions, and these are fermions.
Yes,
right? So you
we
start
got it
with
solved.
the fermion and anti-fermion line. You end with the fermion and anti-fermion line. You have to go between them. Now, does anyone see a really, really easy way to do that? Go ahead. Steve. You wouldn't even have to do this. It's actually slightly easier than that.
Oh my god. This is like the one.
Oh, okay. It's actually easier than that.
I'm just not even.
No, easier than that. Here. This is the easiest way to do it. Yeah.
Oh my god.
Okay, this is technically legal. However, what do you not call this? You don't call it an interaction because there's clearly no interaction going on. So this is not what you want. Okay? That means that relax, it's okay. I see you, but it's okay. So if you have no interaction at all between your lines, that is not what we want. There should be something that connects the lines together. Otherwise, there's no interaction. So, barring that, then, okay. Now, Micah, since you did have your hand up first, can you tell me what you would like to do here?
I want to use the annihilation and pair production to connect both.
Excellent. You can use the annihilation diagram and then connect that to a pair production diagram. In other words, say this photon is the same as this photon, and you chain them together like this.
Yes.
Ta-da! This is a Feynman diagram.
That is the.
You do the same thing with beauty. Wow.
I got a question right.
Okay, good. Now, please make sure that in your notes it looks exactly like this. Not okay, but nicer, but neater. But aside from that, make sure your arrows are all there, pointing the right way. From the right to the left, to the left to the right. Okay, right? Make sure that the arrow pointing to the right is labeled E minus, the one pointing to the left is labeled E plus. Make sure that there's a gamma labeled on your photon line. You still need to label them, mainly because people have different conventions for what thing gets the squiggle, and so some people use different things for different squiggles, so you better label it to make sure. All right, Kyle. Say that one more time. Because these are the initial and final state particles, we put them at the ends of the lines, just those. So we typically just draw like this. That's a good question. Thank you.
What if you use boson other than gamma?
Boson other than photon. We will get there. Don't try to do that until I tell you how to do it.
Oh, wait.
Yeah, we will get there. Don't worry. We'll use all the bosons. Yeah.
All of them, even the Higgs.
Just take the right two electrons, hold them.
You gonna like this?
Yes.
Yeah, no difference at all. Okay,
Okay.
order, this axis means nothing, okay? So the order in this direction means nothing. So another perfectly equivalent diagram would be, for example, this. And this is not even a different diagram. Like, you don't even know that. Oh, wait, actually, technically it is. But we don't need to worry about it. Okay. We're going to do the calculations even better, but don't worry about that part. Okay. All right, good. Now, yeah, sorry.
On the left-hand side, shouldn't that be a... Never mind.
Okay.
I
I'm pretty
answered
sure
my
this
own
is the right
question.
way.
Yeah, that is.
Good. All right, good. All right, now, this, however, is not the only diagram you can draw to do this one. Let's do another one. Same interaction. So, a suggestion for another way we can do it?
But I think you rotate the diagram.
So, what does that mean? Yeah, describe what it will look like.
I don't know.
Okay, well, you're actually right. You can kind of do it just by rotating.
You have to do the top so you interact with
Okay, good. So let's put that in terms of time going from left to right, though. So what's it actually doing then? See, for you? Say it again? Almost. You can have two absorptions. You need to make a photon first. So what do you need? An emission, then an absorption, right? You could emit a photon and then later absorb the photon. Like so. Electron here emits a photon. Positron here absorbs the photon. See it? You need to have the arrows. If you forget an arrow like here, I'll forgive you, that's fine. That was pretty clear, right? You do need the arrows on there somewhere. And for correctness, you should draw on both sides of the vertex. But sometimes you might forget, it's not a big deal. Okay, do you see that? Okay, actually, this is actually called S channel, this is called T channel. You don't need to worry about that. So these are two different ways of drawing the same vertex. There's actually plenty more ways. There's actually an infinite number of ways of drawing each interaction. We are not going to draw the infinite number of ways. It takes a while. Instead, we are going to draw the simplest diagram. Okay? So your goal is always the simplest diagram. And the way I am going to refer to the simplest is, is called leading order. And what does simplest mean? Fewest vertices. Okay? You can always, it's easy to add more vertices into a diagram. We want the fewest possible. So I use the word leading order to describe that. Okay, that's the math term. Yes, the name. Yeah, so these are both cool. Okay? But you could do one with 4 vertices, and that would be legal, but not leading order. Mike?
So, is it possible for the leading order to be the same thing as annihilation pair production, but without the photon in the middle? Just omit that part of the production, and it goes down.
Like this?
Yeah, so then you would have
This is
one,
the-
and it would include a vertex. So, omission of the actual photon itself. It goes electron, positron, positron,
What would the
electron.
boson be?
No, you can't do that. You can't have a vertex like that. Right?
Okay.
The vertex must have a one boson, 2 permeables.
Oh yeah.
It's good. I'm glad you're thinking of that. No, that's a good question. If there's multiple ones that fit the bill, just do one. It's fine. Okay.
Wait. That. Never mind.
Micah forgot the gamma sign.
I forgot the gamma sign.
Okay. All right. So, let me have to erase some of this. Have you seen the boards in the upstairs labs?
Maybe you should be taught this.
You see the two whiteboards? They're
You
nice.
should be taught the paper confinement.
Gigantic. In the
Wait, say that again?
science labs?
Future
You have some science labs?
Actually,
I guarantee I'll remember that day. Probably won't remember the lesson though.
Oh, no, I mean in the classrooms.
Wait, why would you want
The
to?
classrooms?
no,
Yeah.
that was what's funny because future confinement.
They're real nice.
All the time with this students.
They're like from the
Like,
floor
hey,
to
you guys
floor to
can do some
ceiling,
study,
like wall to wall.
and they'd be like, yeah, sure, let's study some quantum
But
physics.
different from
Yeah, we'll do that
whiteboard
too.
paper, the much nicer material, so it costs a lot of understanding. They're really
He
nice.
sounds like a really
Not
great
sure why
teacher.
I
It's so
but
jealousy.
no, it actually predates ISIS and stuff. We've been trying to get that stuff remodeled for a while. Remember the old labs? No, you're too young. Seniors, all right, seniors. Okay. I can remember back in my day. No, they were really ugly though. Not very functional. The old pad room, though, you guys have never had a chance to take a pad in the old room. It's awful. It's like no space. It's like a third the size of this
My
room.
binders.
Like everyone's like crowded in there, trying to do dissections and stuff. Okay, we got it. Yeah, basically, that's how they study it. Okay, let's talk about composite particles. Okay?
Wait,
You
what's
might
the
have an
leading order?
interaction, for example.
Just the leading
You might have an interaction that looks like
It just means
this.
that it's the simplest it has fewest vertices.
But I want to know what it is for
This
this.
is pretty easy.
That's what it is.
Okay? So what's that say? It's pi minus pi plus goes to proton, antiproton. Okay, now, these are not fundamental particles. Only fundamental particles interact. So let's say all the interactions are at the fundamental level. So the first thing you need to do is break these into their constituent quarks. Okay, these are made up of quarks, which you can do by pulling off that handy-dandy little thing.
Okay. Yep.
You know, the particle list that I gave you, right? So you look at it and you say, okay,
Where's pi?
pi plus is on
There
there,
it is.
right?
Pi.
What's a pi plus? Go ahead.
No, never mind.
No. What's a pi plus, Ish?
Shh. I don't know
Good
what
job.
a UD
Up,
is.
anti-down. So pi plus
Name.
is up, anti-down. And here's how I represent this. See, I put the name of the particle,
Yeah.
little bracket, and then the actual quark.
Leave me alone.
No.
I don't need this in my life.
Okay. Now, pi minus is not on the sheet, but what's the core content of a pi minus?
Probably the opposite.
It's the opposite of this, right? So it's anti-up and down. Okay, what's the core content of a proton? Up, you look it up, it's up, down.
Up, down, touch,
An antiproton, therefore, would be anti-up, anti-up, anti-down. Please don't fall into the trap of thinking that up is the opposite of down. It's not. I know, right?
The opposite of bottom.
It's up, the opposite of up is anti-up, of course. So, exactly.
Come today.
All right, now to do this diagram, you know what? Let me sweat on this a little bit. Maybe I'll let you sweat on this one a little bit.
Please don't.
Let me do an easier one first.
No! I was looking forward to
I
that.
just wrote all that stuff down.
All right.
Did you have to?
All right, let's do K dot bar. What's a K dot? Go ahead.
K up is up and a strange, anti-strange.
No, down and
I'm looking at it. It says up and an anti-strange.
plus.
Oh.
So what is it?
Down and anti-strange.
Down anti-strange. So K is
You might need to sleep
a
more.
down anti-strange. And
Boy,
K
that's
dot
not
bar is the opposite of that. So down bar, strange. Right? So first you break them up into their constituent particles. Then you draw the diagram. Okay? So here's the thing, when you draw this, now you have a lot more particles to deal with, right? Okay, first thing you should do is
Panic.
not every single one of these quarks has to interact. You really just need one per particle, which happens just about by itself. So you can connect lines that will work easily. That's to say, here's a down. You can just do that. That's cool.
Nice.
Okay? Here's a T-bar, here's a T-bar, you can just do this, making sure the arrow goes the other way, right? That's an anti-particle. Okay? Good, so you took care of those downs. Now here you have a UU bar, here you have an SS bar. What can we do?
Same thing we did.
Which is what?
The absorption.
Good.
Yeah.
You can annihilate. Okay. Annihilate and paraphrase.
Oh, I was thinking that.
Do you notice that I cross over lines sometimes? That's fine.
What do you say?
It's easy to tell where the vertices are, don't you think?
No.
Well, it is. No, because this could not be a vertex, there's no boson on it, right? So I know it's not a vertex, so I just let it cross over.
What? Oh.
It's fine.
Do we need the gamma sign for the?
Yes, thank you. All right.
But the thingies don't have bosons.
What?
That thing with some of
The D and the D
Those
and
are
the
interactions.
D and the D. They
Do you
don't-
notice how
those
they're
are
not interacting
interactions.
with any other particles?
Yeah, you don't have to interact with every single quark in the particle.
Those are
You
actual
need one of the quarks to interact with.
I think you need more sleep than I do. Okay, that's not good.
Should be
Or
impossible.
like, you guys have to help keep it safe.
You read more than 0.
Okay. All right, let's do one more thing, and that is to introduce another particle. Good news is it works the exact same way.
Which one?
Okay, that's the gluon. Gluon.
The gluon.
I thought you said gluon. I was real confused and real scared.
Character
I'd say
G,
gluon.
and it's like a spirally thing, like a spring sort
Not
of.
to say that I'm not still scared for gluon.
You should be scared. It's a gluon.
Exactly.
What you do with a gluon, exactly the same thing as a photon.
Except different.
No, exactly the same thing. So you're like, wait a minute, okay, there's only one thing that is different, and that is what they're allowed to form a vertex with. Okay?
Oh.
Photons can only form a vertex with charged particles. That's good because most particles are charged. Electrons are charged, quarks are charged, no big deal, right? Gluons can be used only with quarks.
Wait.
Well, not quite. Quarks are charged.
Oh, okay.
Right? Quarks have charge. There's only one fundamental particle that doesn't have charge, which is what?
Neutrinos.
Neutrinos. Okay, so photons cannot go to neutrinos. Gluons also can, because they only go with quarks. So you're like, wait a minute, if quarks are charged, then why don't you just, okay, but the gluon carries which force? The strong force. So you can look at the thing, it says strong force. The strong, which do you think is stronger? The electromagnetic force or the strong force? The strong force is stronger, hence the name. Okay, from what you
Just
got it right, it
electromagnetic
makes sense. And the strong force means that you should prefer the stronger force. Okay, so here is number 1, here is number 2. Let's say use gluons when you can, and then use photons if you must. So why do they use photons?
Why do they call it a strong force?
Like what? Electrons, for example, are not quarks, right? So you couldn't use them with the gluon, but you use electrons with the photon. So here, really, the better way to draw this diagram, since these are quarks, is to put a gluon there. With quarks, you should use gluons. With other things like electrons and muons, you should use photons. Then,
Why do we call it the strong force?
what'd you say?
Why do we call it the strong force?
Because it's strong. Good answer, right?
So specific.
Okay, for your homework, I'm going to put up 10 interactions. You first must check the interaction, make sure it's possible. If it's not possible, you can't